Today I will be discussing the constant velocity lab. First, the introduction. The purpose was to construct a computational model to depict the constant velocity of a moving object. In this case, I used a pencil rolling across my desk. To use the momentum principle in Newton's second law to determine if a net force was acting on a system of a moving object. The models used. The experiment is modeled around the momentum principle, a rearrangement of Newton's second law, and its variations, such as the position update formula. By the momentum principle, if a net force exerted on a system by its surroundings is zero, the change in momentum should also be zero. This also connects with Newton's first law, the law of inertia. A preview of the results. The observed position versus time graph calculated from the recorded motion of the pencil is highly like the computational model created in GlowScript of that motion. The variation can be explained by unaccounted net forces acting upon the pencil in the direction of motion. The system versus surroundings. The system is the pencil, and the relevant surroundings are the table that the pencil is on, moving on, air resistance, and the earth. A brief sketch of it is shown below. The initial condition. The mass of the pencil is 0.007 kilograms. The beginning position is at vector 0, 0, 0. The pencil is moving at the right after having had a light push, and the pencil is moving at an initial velocity of 0.15 meters per second. The assumptions that I made, whether friction, air resistant, or negligible, the table the pencil is on is perfectly smooth, and the initial push of the pencil and acceleration up to the starting velocity in the video will not impact the motion of the pencil. Below is a free body diagram showing the force of gravity and the normal force that opposes it of the same magnitude on the object. The details of the experiment. The pencil begins its recorded motion at vector 0, 0, 0 and ends its recorded motion at 0.305 meters 0, 0. The origin and tracker was set up so that the x-axis is aligned with the motion of the pencil and the pencil is started at the origin. Because the pencil is moving in the rightward direction, the motion was measured as being in the positive x direction. And here's a video of the pencil moving. The details of the code. In editing the code, I had to input the mass of the pencil. I changed the initial velocity vector from 0, 0, 0 to 0.15 meters per second 0, 0. I changed the time to run a while loop until it hit time of 1.88 seconds, right about before the pencil hits the laptop and stops. I still left the net force vector at 0 as we are assuming there is no net force, and I changed the position update formula to the velocity vector at a constant ball.vel divided by 30.15, which was the frame rate 0, 0. Below is the position update formula, and below that is the code, which will also be in the description. Here is the observed position and predicted position versus time graph. Red is the observed and orange is the predicted. Discussion of results. The data gathered was in steps of 0.033 seconds from the initial time to final time. While the two lines are very similar, we can observe that the computational model seems to be moving at a rate slightly slower than the actual motion of the pencil until near the end of the motion, when the observed velocity appears to slow down when it hits the laptop. The predicted computational model follows the actual motion of the pencil very well using our calculated average velocity of 0.15 meters per second. But there is still a difference. The observed motion does not keep the initial velocity the entire time. The momentum principle usage. The momentum principle states that the change in momentum of a system equals the net force acting on the system times the duration of the time that interaction is occurring, as represented if rearranged in the equation above. Rearrangement of Newton's second law to reflect that if no net force is exerted on one system, then momentum should remain constant. Because the mass of the pencil is always constant, if momentum is constant, that means there should be no change in velocity if there is no net force exerted on the system. We only accounted for gravity and normal force on the system, so that must mean the forces we assumed didn't exist to have an impact on the system. Sources of error are the table angle and direction. The most likely explanation for the slight deviation from constant velocity is the table angle and the direction. We assume that the table is perfectly upright, but it most likely has a small tilt, slightly impacting our observed position so that it differed from our prediction position, and it did not have a perfectly constant velocity. The pencil is also not moving perfectly perpendicular or perfectly aligned with the x-axis. What if the axes were interchanged? For our motion, we measured that the pencil is moving in the positive x direction. If we were to flip the axes to imagine it moving in a negative direction, the resulting graph, position versus time, would be flipped a full 180 degrees. Instead of the motions of the graphs moving up and to the right, the motion would proceed downward and to the left, as if the changes in position would now be negative instead of positive. The distance traveled should not change as a result of flipping axes, just the appearance of the graph, and the displacement would be opposite. So what does this mean? In this case, we observed that there are already two known forces that cancel out, the gravity and the normal force in the y dimension. However, the net force takes into consideration the entire surroundings, for example, the Earth. and thus it is not possible to identify all the forces that add up to zero. Conclusions. The observed motions of the object, in this case the pencil, can be predicted well by computational models. By the momentum principle, any net force will cause a slight change in momentum and thus a deviation from the computational model. A movement completely free of forces is highly unreasonable, and thus regular motion will not perfectly adhere to a computational model devoid of a net force.